right, so we're going to do related rates today. Turn to, what page is it? 70 something. 73. Okay. Also, if you're taking the quarter retest, it's going to be in the cafeteria today after school. If you're not and you plan on taking it Friday, then it'll be in my room on Friday. Okay. All right, so related rates are basically when you have functions and multiple things are changing with respect to time. Okay, so not with respect to x anymore, like it's all with respect to time. So you can have different variables such as dy dt, this is the rate that y is changing with respect to time. Dx dt is the rate that x is changing with respect to time. dv dt is the rate that volume is changing over time. And dr dt is the rate that maybe like the radius is changing over time. Okay, so you can have multiple things moving for related rates, and these multiple things moving are all like based on one another. They're all related. So one thing adjusting makes the other thing change as well. Okay. So remember when we did implicit and when we took the derivative of this, we would get dy dx equals, and then we get 10x dx dx minus 6 dx dx, right? But since we're taking the derivative with respect to time now, then it would be 1 dy dt, so it's all with respect to time, equals, and this would be 10x dx dt, not dx dx, minus 6 dx dt, and then plus 0, right? And then it's telling you when x is 4, the rate that x is moving is 2. So we can plug in 4 for x. We can plug in 2 for the rate of x. So we get 80 minus 12, which is 68. So the rate that y is moving with respect to time is 68. If x is moving at a rate of 2. Okay, the hardest part of related rates is that it's usually set within a word problem, but doing all the calculus is easy. The setup is the hardest part. So it's really the algebra that you're going to get all tricked up with. But if you just take it one step at a time and make sure you have the right equation, it shouldn't be that hard. So you always want to draw a figure, and then you're going to assign variables, make an equation that relates the variables, take the derivative with respect to time, and then solve. So let's do an example of that. We've got a 6-meter ladder leaning against a wall. Let's say the bottom is being pushed. Do you want to go in or out? Out? Okay. The bottom is being pushed out at a constant ½ meter per second. How fast is the ladder top sliding when it reaches when it's 5 meters up the wall? So this is an example of the ladder. So here's your ladder. It's leaning 6 meters against the wall, or it's 6 meters high. It's leaning against the wall, and then you've got this x on the bottom, and you want to know the rate that it's sliding. So here's the ladder, and when it's being pushed out, because Aryan chose out, then the rate that y is changing is this. But notice that the x here, it's being pushed and pulled at a constant rate. So this is the same rate, but it's slower up here, and then it gets super fast. The rate of y changing is super fast down here. But the two rates are related. So whatever this is doing changes whatever y is doing. Okay, so you need to start by setting up an equation, or actually drawing a picture to represent the situation. So we'll draw a little triangle. Okay. And on the triangle, I want you to label anything that's moving with a variable. So this is the bottom is moving and the side is moving. So they both need to be labeled with a variable. Anything that's not moving, you label with a constant. Okay, so I can label this length of the ladder as 6 because that's not changing. So I can put in, yes?
Where are you getting all these values? Because like I don't see them anywhere.
A 6-meter ladder is against a wall. And then we don't want to, Jordan, we don't want to plug in 5 for up the wall yet because that's a moving thing. Okay, so x and moving, y, they're both moving, so we won't plug them into our equation. If you want on the side, you can say y equals 5, but don't plug it in yet because that's at a specific location. Okay, this part right here, saying its bottom is being pushed, we went without, at a constant ½ meter per second. That's a rate. So is that the rate of x or is that the rate of y? X, good. So we're going to label that dx dt equals 1/2 meter per second. Use the units to help you decide what it is. Meters per second should be position over time. So let's go with dx dt here. Okay, now we want to know how fast is the ladder top sliding. So how do I figure out how fast the ladder top is sliding? That's what rate? Good. That's dy dt. That's what I want to know, right? Okay, so here I have the rate that I know and I have the rate that I want. We have to set up an equation now that has the variables x and y in it, and only x and y. I don't want any other variables. So give me an equation for this picture that has x's and y's in it. Good. So we go x squared plus y squared equals 6 squared, or 36, right? Okay.
I know that.
Yay! Mr. Plunkett's son is taking AB calculus this year, so he's like learning it with him. So every time he pops into a calculus class, he's like, "So what do you do now?" Okay, so now let's take we have this equation. Now we can take the derivative. We can get 2x dx dt plus 2y dy dt equals 0, which is good because this is a constant thing, so it should be not moving. The rate should not be moving, right? All right, cool. Now that I've taken the derivative, this is the point where I can plug in what I know. So I can plug in, I don't know x yet, so we'll solve for that, but dx dt I know is 1/2. And I went with, this is another thing, I went with positive 1/2 because if the bottom is being pushed out, is x growing or shrinking? Growing. So if x is growing, then your rate will be positive. And if x is shrinking, your rate would be negative. Okay, so we went with positive 1/2 plus 2. Our y is 5, good. And then dy dt equals 0, and we want to solve for dy dt. Now I just have to figure out this x value. So where does this x value come from? Good. So over here we've got to go and we have to solve for x. So x squared plus 5 squared equals 6 squared So 36 minus 25 is 11, so x equals root 11.
Yeah.
All good with that? Okay, now we can put that in here. Alright, so dy dt, the rate that y is changing, equals negative root 11 over 10. And what are the units for dy dt? Y is in meters and time is in seconds, so meters per second. Okay. Did you get it? All right, I want you to try the next one because it's kind of similar. Oops. With the winch, I'll show you a picture. So that I'll help you visualize. But I forgot to give you a value for how fast is the boat moving when the rope is, and then I said dot dot dot. So let's go with rope is, do you want to do 45, 30, 22, or 20.5? 30, okay, I've heard multiple 30s. So let's go with the rope is 30 feet. Okay. All right, here's your visual. Remember, don't put variables for everything that's moving. Anything that's not moving, you can have as a constant and label that on your graph. But anything that's moving, then you don't want to, you want to label anything that's moving with a variable on your picture. This is a boat winch. Oops.
Yeah.
What am I doing?
I was scared.
Guys. Yeah. That was your fault. I'm blaming it on you.
Oh my god, there's so many Meriwether pieces. Wait,
That's okay, yeah.
I don't think he posted it on her, or she must have Elon Musk himself, like, his comment, this is the comment.
X is did you get I don't know what that value
Of course
is.
I clicked that like it's stupid. What was that? Well, I have no idea what it was.
Oh, good job, Arian. This should be
Where's this coming from? I have no idea.
negative.
But it says the speed. I know we think like.
How fast? Yeah, you could go with speed. This would be, give me a negative.
He or she wrote it. I don't know the argument. It's 5 squared.
Wait, but if it's speed, why would it be negative? You can't be negative.
Yeah, I know, you can, but solving for dx dt is negative 6 over root 5. I know, so your answer would be 6 over root 5, but dx dt's value is negative 6 over root 5.
We were almost there.
But they were asking for
One
velocity
negative sign away.
right?
Yes.
Oh, yeah.
Speed actually positive.
I know, but I forgot my fundamental rule of physics. For physics, they don't really care about positive and negative. They just care about my I guess I can help us out.
Okay. So those are two triangle ones. The triangle ones are usually the easier ones. But then sometimes they throw you for a loop with other rates. Sometimes they give you the equation for them, sometimes they don't. But here we have water flowing into a cone. I think most of the time they give it to you, but it wouldn't be bad to memorize the cone and the sphere formula. Okay. So the height is 16. The height is 16 of our cone, and the radius is 4. Okay? Alright, and then we've got water in here. And it's being poured in to the cone. Okay, so it's the water is being poured into the cone, and the cone's original height is 16 and the radius is 4. Okay? So let's first let's label our variables. My height and my radius are both changing, right? So the original height is 16 and the radius is 4, but my water is changing. What's this 2 centimeters cubed per minute? that's the rate of the volume, right? Because it's centimeters cubed. So centimeters cubed is a unit of volume. So dV dt would be 2. And it's flowing in, so we'll make it a positive 2. Okay. How fast is the water level rising? So what do I want to know? I want to know dH dt. Good. The rate that the height is moving. And then it says when it's 5 centimeters deep, so h equals 5. But as it's filling up, then I've got multiple moving things. So I've got volume that's changing, height that's changing, and radius that's changing. So the equation for volume of a cone is, do you remember? One-third pi r squared h, yes. Okay, now here's the problem. If I took the derivative of this, then first of all, I would have to do product rule with this r and h thing right here. Like that r and h, I'd have to do 2r times h plus, and then I would have a dr dt and a dH dt. And in the original set of values that I'm given, I'm not given the rate that r is changing. Okay. So somehow I've got to get rid of r. Here's what you do for anything that's like, usually if it's triangular in shape, you've got to find a relationship. But the relationship of this cone is, if you know this radius is 4 and this height is 16, by geometry, any triangle that you draw within it, right, has the same ratio and height, right? Similar triangles from back in the day, right? So the ratio of the radius to the height is 4 over 16. So the radius equals 1/4 the height always. No matter where you are, whatever the water level is, it will always be 1/4 the height. So now I can rewrite my volume equation in terms of h only. So when I take the derivative, it'll be a lot easier. And yeah, let's simplify it before we go. So volume is 1/48 pi h cubed. Okay. Now taking the derivative is going to be a lot easier now that I only have two variables. dV dt equals 3/48 or 1/16 pi h squared dH dt. And remember, we took the derivative with respect to time, so you need a dV dt and a dH dt. And then we'll plug in 5 for h, 2 for dV dt, so dH dt is equal to, what is this? 1/16 times 2, 32 over 25. Yeah. And what are the units of my, I'm going to erase this real quick, and what are the units of my dH dt? H is in centimeters, and time is in seconds. So we'll go centimeters per second.
It's not minutes.
Huh?
It's not minutes.
balloon is inflated at 10 centimeters cubed per second. Here's your balloon. That's not a balloon. That's not a balloon.
It could be an oddly shaped balloon.
Yeah, maybe.
That's a balloon.
That's a balloon.
Yeah.
Balloon. This balloon is cool. It's a magic balloon. It changes colors.
Oh my, I don't think that's a real balloon.
How do you think you're able to
I asked you
I don't
if
think, maybe it's just like a
I
special
want that.
changing color.
Don't we all?
Glow in the dark.
I love color changing things. Okay. Spherical balloon. Let's draw a sphere. Not very good at drawing circles. What's a sphere like? It's like one of those punching bag balloons. Do you remember those? With the rubber band on the other side. It's so fun. I'm gonna draw things this way too. No, you don't have to draw. Okay. Volume of a sphere. Oh, this is dVdt because it's centimeters cubed. And then how fast is the radius changing? So we want to know drdt. And then when the diameter is 1, so that is r equals 1/2. Okay. All right. Let's make our equation. Volume of a sphere is, wow. Nice job.
Yeah, I think that's one of my best.
Okay. Now, here's what the nice thing is. We have dVdt and we want to know drdt, so I don't have to replace any variables here. We can just go straight to taking the derivative with respect to time. Okay, and now we can plug in 10 for dVdt, 1/2 in for r, and then we can solve for drdt. This one's easy. Let's go units. R is in centimeters, and T is in seconds. Okay? All right, I don't have a picture of this fish problem. Well, I had the program of the others, and then I wrote the notes based on the program so that you could visualize it. And now, training wheels off. You just reel in this fish, guys. Okay. Here we have a fish. There's my fish. It's reeled in at a rate of 2 feet per second. So this R is changing. The bridge is 16. And then at what rate is the angle between the line and the water changing? That's this. Theta. Okay, let's label what we know. So we know that drdt is what? Let's go negative 2 feet per second. Because it's being reeled in, so it's getting smaller. Okay, then we've got the bridge that stays constant. We want to know the rate of the angle, so we want to know d theta dt. Sure.
If you're reeling in the line, would it be above the water?
The fish?
Like you're like whenever you make bigger,
Like you'd be standing on top of the bridge, and so it'd be a little higher than the.
No, you're like right on the bridge. You're like laying down on the bridge. You're tired. You've had a long day.
Just to fit the
Huh?
math question already.
Yeah, exactly.
and it goes above the water.
No, you're like laying down. Don't poke holes in this problem just because there's no visual. My problem is unholable.
You pass up the line and then you put it pull down to go.
Yeah, exactly. And it's self-reeling.
Yeah.
You press the button, it reels itself in at a constant rate. Yes, at a constant rate. You know, guys, these are the training wheels that you must have on until you can. There's too many. We can't add so many variables in here.
Yeah.
You're not ready for it yet.
So what does it look like when it's changing? Like if that is bigger.
The angle's getting bigger because the fish is moving towards the dock. It's not that hard to visualize, is it? Fish is swimming. Look, I'll put little swimming motions. Now you know.
Wait, but you already
But you're reeling it in.
You're gonna look back.
And it stays in the water. You can't just pull a fish straight out of water, like diagonally. That's not how it works. You have to reel it in first and then you pull it up. Have you ever been fishing? Obviously not. I fish all the time. Yesterday, I fished yesterday. That's how I caught my dinner. And I reeled it in at a rate of 2 feet per second, guys. I was on a bridge that was 16 feet high. These are real world problems that we're doing. No, it's not. 16 feet is not tall. A tall bridge. It's like a short bridge. That's like 3 people high. No? 4 people high.
It's taller than what I normally.
Okay.
3 8-foot tall.
I need an angle with R and theta. Oh, yes.
This is where the
Yeah. You should know this problem because guess what? We're in the trig unit and then it's a related rates problem. So this is like a 2-for-1 deal for me on a test, right? To like ask you a problem like this, I can test your trig and I can test your related rates. Okay, derivative of sine is cosine theta. We need a d theta dt because we took the derivative of theta by chain rule. And then 16 over r, you could do quotient rule, which is fine, but not smart. You should just make this 16r to the -1, so it would be -16 over r squared, right? Better than doing quotient rule. Then I'm missing a dr dt, yeah. Okay, cool. I can plug in 20 for r. And I can plug in -2 for dr dt. But how do I figure out what cosine theta is? So if r is equal to 20, then I don't need to find this angle. Like I don't do sine inverse on your calculator. of 16 over 20. All I need is this side because I can figure out cosine of that angle pretty easily. If this is 16, that's 20. This is yeah, it's a 3, 4, 5 triangle, only bigger. So this will be
Yeah. 12.
they're all multiples of 4.
Wait, what do we land?
I don't want theta though. All I need is cosine of theta. Which if I find this side, I have cosine of theta. I can do 12 over 20. You see what I'm saying? Like, you don't have to solve for the angle. You just need to know cosine of the angle. Okay. Did somebody give me the answer? What'd you say, Jordan?
No problem.
Okay. Anybody? I don't remember the answer to this one. Thanks. Positive. Yeah, theta's. Okay, 2 over 15, and then theta is in radians, and then 15 is in seconds. Radians, time is in seconds. Radians per second. Cool? Okay, last one is a challenge problem. And then I'll let you finish your corrections or start on your H-dubs. This is, I don't really like the way this is worded, so don't poke holes in this problem, because I didn't really make it, but I kind of like it. Here's our lamppost. How high is the lamppost is 15. Is this the right thing? Oh no, the light pole is 16 in this problem. Is the guy 6 feet tall? Yeah, he's 6 feet tall. He's walking towards the lamp? Okay. Well, at least you have a visual. Yeah, we're always in radians in this class. Yeah, I don't have the ability to just, this is as best as I can do. That's how he walks. He just rotates. His like arms are like this, and he's like the whole time. Isn't that how you walk? That's how I walk.
I see him moving.
You see him walking? Yeah, it does, but doesn't it look like he's rotating
If you choose to look at it that
on
way.
You can look at it like
on like a stick?
You can also look. It also kind of looks like he's like jumping forward and like.
Oh
Looks
yeah.
like he's like clapping and like.
It's kind of fun. That's how we should all walk. Just like constant like.
Everyone is jumping out of
Okay, I'm done. Enough coffee today, guys. Okay. So there's 2 problems for this one. The first one, well, these are similar triangles. For this first one, we want to know the rate of the tip of his shadow moving. That's this distance. From here to here. Okay, this guy is 6 feet tall, so this never changes. And the light pole is 16. And the rate that he is walking is 5. So let's label this from here to here, y. Okay, are you with me there? Okay, so I need to know dx dt. That's the one that this is asking. And I know that he's walking at a rate of, is he walking towards the light? So -5. Okay. So let's start by, we know that this is the same situation as this, where we've got similar triangles, right? So the ratios are the same of the two triangles. So what's my equation that I can set up? Yeah, I'm going to go x over 16 so I can keep the variables on top, but that's fine. So x over 16 equals, and then how do I get this small triangle? Yeah, x minus y over 6. Cool. So I've got a similar triangle ratio. Now I can easily solve this. Actually, I'll go over here and make this 1/16 x equals 1/6 x minus 1/6 y. It'll be easier for us to take the derivative of. Okay, so now we've got 1/16 dx dt equals 1/6 dx dt, and I really could have brought the 1/6 over, but that's okay. Minus 1/6 dy dt. And then we can plug in, what can I plug in? -5 for dy dt. So 1/16 minus 1/6. I'm going to bring that over. Dx dt equals plugging in -5, positive 5, 6. That's it, right? Can somebody solve that for me? Oh, you make it 6x equals 16x minus 16y. Yeah, you can do that too. Probably would be easier. What? -8. Thank you. Feet per second. Okay. And then the last problem is at what rate, so I spelled that wrong, is the length of his shadow moving. So that, for this picture, we want to know, this is still 6 and this is still 16, but we want to know this. Like, so we know this is still y, but this is what we want to solve for. The length of his shadow moving, so we want that dx dt. So our equation would just be set up a little bit differently. It would be x over 6 equals x plus y over 16. And then let's do it Aryan's way and cross multiply. looks easier. Yeah, and then let's go ahead and subtract. Now we can take the derivative. 10 dx dt equals 6 dy dt. And then dy dt is negative 5. Ooh, much easier, Arnie. Negative 3 feet per second. Okay, that was fun. Good times had by all. Or maybe just me. Okay. Any questions on related rates? All right. Your homework for tonight, do it on a separate sheet of paper. Don't do it on that paper. I bet you somebody's going to turn it in on that paper. I bet you. I would bet you money, but I don't have any money. 1/4. Somebody's going to turn it in on that paper. So try do the questions on a separate sheet of paper. The answers are on the back of the paper, so you can check your answers as you're doing it. Isn't that fun? Okay. No, I told you, do it on a separate sheet of paper. Do you want a quarter or not? What, you think I'm made of money?